Now that we have all of our derivative rules, let's see if we can practice putting them together. So let's start with this. Log base 10 of cosine of 4x. I hope by now you're recognizing this is going to be a chain rule problem. We've got log base 10 of some function. We just figured out our derivative rule for log base b. I'll just remind you it was d dx equal the d dx of log base b of x was 1 over x ln b. So in place of x here, we have this more complicated function, cosine of 4x, but that doesn't bother us because we know the chain rule. So it becomes 1 over cosine of 4x times ln of b, and in this case, our b was 10. But we're not done yet. Chain rule says now we move our way inside. Take the derivative of cosine, which we know is negative sine, and as always in the chain rule, the inner function, in this case 4x, doesn't change. And then we're almost done. Chain rule says take the derivative of the innermost function, which is 4. What rule or rules are we going to need for this one? We've got x to the 7th arctan of 4x cubed. So we've got a product happening here, x to the 7th times this stuff, and one piece of the product rule involves the chain rule. So the derivative of x to the 7th from our power rule is 7x to the 6th, and then we leave the other piece unchanged. And then in the second half of the product rule, we leave the x to the 7th alone. And then we've got to take the derivative of arctangent. We just figured that out. I'll remind you what it is. That's 1 over 1 plus x squared. And again, we don't just have x in here, but since we know the chain rule, that doesn't faze us at all. We write it as 1 over 1 plus whatever that inner function, 4x cubed, is squared. And are we done? I hope you're saying no, because we need a chain rule here. We've got arctangent of something, so it's 1 over 1 plus the very same something squared, but then times the derivative of that inside function, and the derivative of 4x cubed is 12x squared. How about this one? Sine of ln of arc cosine of x to the 5th. So this is another multiple chain rule, right? When you read this out loud, you keep saying of all the way through. So there's no multiplication. This is all chain rule going on here. And we've always been starting from the outside with chain rule. So we've got sine of a bunch of stuff. What's the derivative of sine of a bunch of stuff? It's cosine of the very same bunch of stuff. So we don't change the inside. Now we're done with the sine. Don't even let it distract you. Now you've got ln of something. And remember, we just figured out a little while ago that the derivative of ln of x is 1 over x. So this becomes 1 over all of that stuff, arc cosine of x to the 5th. But we're not done yet, because now we have to take the derivative of the arc cosine. And we just figured out a little while ago that the derivative of arc cosine, I guess we didn't figure it out, we told you what it was, and we left it to you to figure out, was negative 1 over the square root of 1 minus x squared. So what should we be putting here? We should be putting negative 1 over the square root of 1 minus what? We don't just have x, we have x to the 5th, so it should be x to the 5th all squared in there. So the sine became cosine, the inside stuff didn't change. The ln became 1 over, the inside stuff didn't change. The arc cosine became negative 1 over the square root of 1 minus the inside squared. Again, the inside didn't change, and then we have one last innermost function, x to the 5th, its derivative is 5x to the 4th. All right. And why did we leave this one for last? It seems surprisingly simple compared to the other ones, and it is. But it is one interesting thing about it that I want us to think about. And we have an applet for you to use to explore that. So we've got ln of something. So by our rule here, the derivative ln of something should be 1 over the very same something. And then the chain rule says take the derivative of the inside. The derivative of 5x is 5. So let's contrast this to when we had a function sometime earlier. I think we did sine of 5x a little while ago. And its derivative was cosine of 5x times 5, right? What happens here? The 5's cancel, and we just end up with 1 over x. So it's as if the 5 didn't make any difference. If I had put a 55, if I had put a million, if I had put 23.6, no matter what, they would have all canceled, and I would have gotten 1 over x. Whereas here, putting the 5 in definitely made a difference, right? If I'd put a 3 here, I would have gotten a different answer. So why is it that this 5 doesn't make any difference? That the log of 5x, the log of 6x, the log of 7x, the log of 1,000x all give you the same answer of 1 over x. You should be a little wondering about that. Why is that? So what would it mean for two functions? We've talked about this when we were sketching derivatives. If there are two different functions that have this same derivative, 1 over x, in other words, ln of 5x and ln of x, they both have the derivative 1 over x. What does that mean about how the graphs of ln of x and ln of 5x are related to each other? They have the same slope at every point. That means those two graphs have the same shape, but they might be differently positioned vertically, meaning one might be the other one shifted up or down. So can you use a log rule to see why that is true? How could we have written ln of 5x, rewritten that, using a log rule? We could have rewritten that as what? Ln of 5 plus ln of x. So in fact, ln of 5x is the graph of ln of x, shifted vertically by a distance of ln of 5. Take a minute to think about this. We know that multiplying by a 5 on the inside from our very first day does what? That squeezes the graph horizontally. Adding an ln of 5 does what? Shifts the graph vertically. So this says that the natural log has this very, very special property that a horizontal shrinking is the same as a vertical shift. Do you know any other functions where a horizontal shrink is the same as a vertical shift? That certainly won't be true for sine or exponentials or anything like that. It's a very special property of log functions, and we have an applet for you to play around with by doing this to see graphically how that works out. So please go ahead and explore that applet, and then we'll have one more way to take derivatives.